Okay, welcome back everybody. This next talk will be a very interesting piece on random number generators and what can go wrong with them. Please welcome Pseudoleon presenting Roll for Encryption.
Thank you. As mentioned, it's going to be a short talk about random number generators, what can go wrong with them, and in general, we're going to have a few interactive sections as well, so you can see just how horrible randomness really is. A bit about me. I am associated or interested in some of these things. If any of them ring a bell, then come chat with me after the talk. And moving on to the actual talk. At the core of randomness, we want numbers. We want random numbers, and when we run this command in a terminal, echo random, we get a random 16-bit number, I believe. Maybe different on different operating systems, so forth, but 16 bits probably. And the big question is, okay, how are we getting these 16 bits? Where are we getting randomness from? How do we source randomness, and do we care always about the source of randomness? In general, most things in nature just aren't random. If I repeat an experiment, it's probably going to give me the same results under the same conditions. There are some exceptions to this, depending on your viewpoint. For instance, we believe radioactive decay is actually completely random. We believe that various parts of quantum mechanics are completely random. And there are various processes in nature that we believe if we just look at, the results cannot be predicted, and they are completely random, and we accept that. On the other side of the coin, besides this true randomness, there is a pseudo-randomness, our attempts at emulating this true randomness that you can maybe find in nature. Pseudo-randomness is, in general, something that we need surprisingly frequently. We can't always rely on complete randomness, because even if we could easily and cheaply get complete and true randomness, the problem is we sometimes actually want our source of randomness to be deterministic. We want the ability that, given a state, we can predict the next few states. This is something that's very appreciable in various how cryptographic, how non-cryptographic applications, and pseudo-randomness as an artificial thing is very useful. And besides it being deterministic, we also care about it being repeatable. Okay, we can set our pseudo-random generator to some certain state, and we can generate and predict what values we'll get. But we also want to be able to set it to these states reliably and repeatably and consistently. So these are the properties that make pseudo-randomness different from true randomness. There's examples of both. As I mentioned, radioactive decay, quantum mechanics for most perspectives, and even the distribution of stars in the night sky can be seen as being truly random. While some examples of pseudo-randomness are lava lamps, there's a famous wall of entropy found in the Cloudflare HQ that some may be aware of. There's a hardware entropy. We just look at the CPU cycles, interrupts, what's happening down the processor level, and just sample that for some sort of randomness. And that's also pseudo-random because it's deterministic in a way. If you know enough information, we can predict it. It's repeatable, maybe sometimes. Repeatability is more of a trait we want pseudo-randomness to have than something it necessarily does have. And finally, pseudo-random number generators, because it's in the name. We want to be pseudo-random. As far as pseudo-randomness is concerned, we do sometimes genuinely want things to be pseudo-random. We don't always want things to be completely random. For instance, if you read XKCD comics, like the one on the left, if you click the random button, one may expect it to just give you a random comic, and that's that. In reality, that's not how it works. Randall is a clever guy, and he coded the website such that when you click random, it actually checks what comics have you seen before and filters those out, and it tries to find comics that are a certain distance away from your current comic as well. So it doesn't want to show you repeatedly like newer comics. If you're on a new comic, it'll show you an older one and so forth. And this is all pseudo-randomness because it's obviously going against what true randomness should be. It should be very uniform, it should be very unpredictable. Well, here there's some type of rules already in place. Similarly, if you listen to Spotify or iTunes or whatever, if you click shuffle, it's not going to be random. It's actually quite a horrific algorithm. Spotify published how their shuffling works in 2014, and now deleted the article actually. And the TLDR was that it would first shuffle, it would take the set of all artists in a playlist, would shuffle them, and then would attach a few songs to each artist, and then would shuffle those songs, and then would add any songs that weren't in the original playlist or that weren't part of the initial attachment of songs to artists. All in all, what it results in is the genres flipping way too much and artists being sometimes too consistent at times. If you ever had any complaints about Spotify Shuffle being bad, it's because they try to make it not random. And believe it or not, from some testing, if you do make it truly random, it's actually even worse. You don't want your playlist to be truly random usually. And it's very common in video games as well. This is a screenshot from Baldur's Gate that, in a way, kind of inspired the name of this talk, Roll for Encryption. Because in Baldur's Gate, there's an option that, I'm not sure if it's a default, but it's an option called Karmic Dice, where the idea is that the dice rolls aren't truly random. Instead, if you roll a bad roll, then it's more likely you're going to get a good roll later on. Because this is what people expect when they hear random. If I'm getting bad rolls now, I'm going to get good rolls later. This is some type of expectance. We expect things to be uniform, or for the good to be met with the bad, and the bad to be met with the good. But in practice, isn't really how it holds, and people in general have a rather poor perception of randomness, or of what random behavior really looks like. So we're going to do a quick interactive little bit now. We've got two images here, yeah? We've got A and B. One image is completely randomly generated. It's just random dots scattered on a screen. The other depicts how certain worms in a cave in New Zealand behave. And they have a very strict pattern in how they behave. So the question is, which of these images has a pattern that you can notice, and which one is completely random? Let's go with a quick poll, I guess. If you believe it's A that's completely random, raise your hand. Okay, we've got, I'd say, 2/3 maybe, yeah? 2/3 for A, 1/3 for B. The truth is, yeah, A is the completely random one, and B is the glowworms. This may be a bit surprising, because, hey, this one looks a lot more uniform. Why isn't that one a random one? And the answer is, it's too uniform. The dots are too balanced. They're placed in a too well-ordered of a way. And actually, if you see a species with this type of distribution, it's a very territorial species, because they don't like sharing space. Every dot has a certain distance around it. They're very adamant about having their space, which is why if you find a random distribution in, let's say, nature and with some other glowworms, that means they're not territorial. They're willing to share space, and their random distribution is actually something that tells you a lot more about their biology than this one. And in general, people have a very wrong perception of what randomness looks like. So much so, it's an entire fallacy called the clustering illusion, where people think that objects that are evenly clustered are more random than ones that aren't. And we did technically fool 1/3 of the people in the audience with this, so I think the illusion still holds, even with people who do interact with randomness more often. As for randomness in practice, we've got various programming languages implementing various pseudo-random number generators in practice. These are some of the more popular ones I managed to find in a very quick skim. I'm doing a bit of cheating here, because while yes, let's say Golang and C and Java do implement something called an LCG that we'll explain in a moment, they do it in a bit of a different way, with different constants and even different ways of filtering the results. So me saying they're the same is kind of but good enough for now. In general, the two most popular pseudo-random number generators that you'll see in most programming languages are linear congruential generators, those being LCGs, as seen in Java, C, Golang. I'm thinking what else? Probably not much else. Hopefully, they're really bad. We'll get to that later. The other more popular or more modern variant are Mersenne twisters. Mersenne twisters are a bit more memory intensive, as we'll see also a bit later. And they're popular in Python, and C++ offers a standard library implementation. And many other modern programming languages offer Mersenne twisters as either a default or as an option, because they're surprisingly good. In comparison to an LCG, they're really, really good. One language I've excluded from here is actually Rust. And the reason I've done that is because Rust is a bit special. Rust is one of the very few languages that if you just call randomness in Rust, it's actually not going to be a pseudorandom number generator. It's not going to be a normal one. What it's going to be is its own custom one that's, as far as they believe and the scientific community believes, is actually cryptographically secure, which is both a good and a bad thing, because it does mean it's slower, but the security issues it fixes by chance are really, really worth the slowness in efficiency. So all in all, a very good thing. So first we're going to talk about LCGs, the linear congruential generators. This is going to be, I'm going to try to really not dive into the math of these or the Mersenne twisters because it's not too important. What is important is the actual name. So it's linear, which means it's a linear operation. We got one multiplication, we got one addition. It's congruential because it's all modulo something. In this case, it's modulo on n. N is usually either a prime, or if it's not a prime, it's a power of 2. The reason for this, for it being a prime, is because it makes things a lot easier on the mathematical side of things. Primes are very nice numbers, especially in modular arithmetic. And if you can do things modulo primes rather than modulo composites, it's a very beneficial thing. However, for efficiency reasons, we really, really, really like powers of 2. If n is a power of 2, then if we just multiply x by a and add b and check the new number, what we can just do to just do the modular reduction, we can just take the bottom n bits, and that's that. And it's a very easy and nice way of doing modular reduction by just taking bits. That's very fast. Most programming languages implement this with, I think, powers of 2. I think C is an exception, maybe. And some of them use either 32 bits or 48 bits, more or less. And yeah, in general, how it works is there's an internal state, x, that gets updated in every iteration. And x is also then outputted, usually in its entirety, to the people calling the generator. Now this is a bit of a problem because, okay, as mentioned earlier, it's actually easy to implement. It's very simple, as you saw just a moment ago. It's quick to run. One multiplication, one addition, one mov operation, I guess. And it's statistically very, very solid. If you look at and compare pseudorandom number generators, all the ones that are being used in how programming languages, how in industrial applications, whatever, LCGs are actually, despite their very, very simple structure, probably one of the best ones. They pass pretty much, with good parameters, they pass every statistical test you can imagine. They're really good, they're really uniform, they're really evenly distributed. They have so many nice statistical properties that we just love using them. It's a shame they suck from the security standpoint of things, though, because let's say we call an LCG, we get x of n minus 1, and then the program calls it again. Knowing the parameters a, b, and n, it's very easy for us to just, keep repeating it and find what the new values are going to be, which means that if we leak to some type of attack, or even just one value of x in its entirety, then we've leaked the entire internal state of the LCG in effect, and we can just, generate our own values and know what the server is going to be doing. There you can do some things. You can make A and B hidden. Having n hidden is usually a waste of time, and most of the time you're going to have it be a power of 2, it doesn't really matter. But you can hide A and B, and you can pretend that's going to keep you safe. But again, it's a linear equation. If you collect a few samples of x, especially consecutive ones, you just solve a couple linear equations, you recover x, A, and b. That's that. So from a security standpoint, if it even offers any, it's quite poor. What some languages do, I know Java does it as far as the popular ones go, is that instead of giving you the entire x, they actually give you only the top or the bottom n bits. And this is useful because if we just recover a few bits, it's not necessarily game over in just a few queries, because it's a bit more difficult to predict the next values if you don't have the entire state. But this is also something that can be solved, and it's not terribly good security practice either. It didn't even originate as a security practice. Originally, it originated as a method to make it more statistically solid. Because with some parameters, the bottom few bits would actually have a very strong bias. I think a very obvious example is, let's say n is a power of 2, and a is some even number, and b is maybe some even number as well. We multiply x by an even number, the last bit is going to be a 0. We add b, which is also an even number, the last bit is going to be a 0. We do it modulo n, we just take the bottom n bits, well, modulo 2 to the n, but yeah. And then the last bit is just going to always be a 0, and that sucks. That's not that random, is it now? And okay, if we set b to be an odd number, it's going to be always a 1, and so on. If we make a an odd number, it's going to be better. In general, we don't like our a and b's to be dividing n, especially our a, which is why we like using primes, because nothing divides a prime besides itself. So that's the motivation behind primes. But again, for efficiency reasons, we prefer just taking powers of 2, using an a and b that are compatible with it, and maybe dropping a few bits for statistical reasons. And if we drop a few bits, it's better. It's a bit better in terms of security, but if we recover a few consistent samples, consecutive samples, I mean, well, we can still recover the state. It's a bit more interesting how to recover it. We use something called lattices. We use various algorithms that are very interesting that I don't have the time to explain now, but they are fun and is how most practical attacks against these types of systems usually work, because in practice, you're not going to be getting the entire output either. It's usually going to be used, okay, we generate a 32-bit number, we're going to use like the bottom 10 bits to generate a coordinate for a video game or whatever, and then that's that. In reality, there's an example where this was broken, a truncated LCG in a video game. That's why I'm mentioning it, and it's Minecraft. The seed finding, the way seeds work in Minecraft is actually they use an LCG to generate the random numbers. They drop a few bits, they do some floating, they do some rounding, so you don't get the full values, but you still get enough that you can recover the seed based off of, so let's say, a few chunks and stuff like that. And that's a fun thing to see and do. There's also something called rejection sampling. It's not really a security standpoint thing, it's more of a, well, it's easier for us to do this than to not do it. And the idea is, okay, we want, let's say, a number that's less than 1,000. And we call the LCG, we take the top 10 bits, yeah? And the problem is 10 bits is 1024. Sometimes it's going to be above 1000. And what can we do? Well, option 1, we can just do a modulus. We can just say, okay, take 1000, take the random number, the low 10 bits, and do it modulo 1000. But that's kind of bad, because then the numbers from, let's say, 0 to 24 are going to be twice as likely as the rest of the numbers in the distribution, and that's not that random, so that's kind of terrible. So instead what we do is if we get a number that's larger than our bounds, we just try again. And because we're looking at this from the bit perspective, in the worst case scenario, we're going to be usually trying again in just a few attempts, so it's not going to be that bad. And if it's especially bad, we can just maybe do it modulo as well and don't care about the fact that some values are going to be not as uniform. And this is actually a common problem as well, that people don't do rejection sampling, but instead do just a modulus, which makes certain distributions not uniform. You get the lower numbers far more likely than the rest. The alternative to LCGs that we saw earlier is the Mersenne twister. Mersenne twister is a complicated mess. The material isn't supposed to be educational, it's supposed to just illustrate that it's a bit complicated. It's more complex than LTG, but it's got some advantages. For starters, it's got a very long period. For context, a period is how many values we can generate until we start getting the same values back. And for Mersenne, this is a very, very big number. This number is actually also called a Mersenne prime, which is where the name comes from. And this is a very good thing. The problem with Mersenne is that it's got a pretty big state size. It's 2.5 kilobytes, because its state is 600 and something 32-bit integers, and that's a very big state. For context, LCG had a state of one 32-bit integer, and I guess some constants to save on the side. So having to save 600 more is frustrating, and the question is then, okay, what's the advantage? Okay, besides the longer period length, an advantage of Mersenne is kind of in how it works. Spoiler for the security, it's not that much more secure, but the simplification of how Mersenne works is that we get some seed, we initialize the seed into a state. How we do this doesn't really particularly matter. It's a random procedure, as annoying as to use that word is. And we get the state, which is 624 32-bit values. And when we want a value from our random number generator, we just say, hey, Mersenne, give me a number. And it's, say, gonna give me the topmost number, the first slot. And if I want a new number, it's gonna be the second slot, and so on. And once it uses up all its 600 slots, it's gonna call its twist method. Here the twister part comes in, which is just a very fancy matrix multiplication that's just gonna mix all of these values together into a new state, and then I can again call Mersenne and tell them, and they're gonna give me, hey, here's this slot, here's this slot, here's this slot. So Mersenne, in terms of performance, can be faster than LCG, because after a twist, it's got 624 values just loaded in, ready to be given and provided to you. But the twist itself is actually quite complex in a sense. It's an entire multiplication of a matrix. There's a lot of linear stuff happening, lots more multiplications than just one as in the LCG. And in some very, very high level overview, you could view Mersenne as just a very complicated LCG, where you've got, instead of a single value, a matrix and just stuff happening. And security-wise, it's not much better in LCGs. It is better because, for starters, the state is 624 values, so the obvious attack on LCGs, where we can just, brute force these states, isn't really possible with Mersenne because it's quite a big brute. But the problem is, if we observe the entire state, let's say state 0, we can just do our own twist and recover state 1 and state 2 and so on. So having an entire state compromised is pretty bad. The other thing with Mersenne is that, okay, but what if you don't get entire state? What if we get half of state 0 and half of state 1? In that case, it's actually a lot more complex, and it may not even be possible to recover the state for the attacker, but it's not impossible, always. As I mentioned earlier, there's linear transformations happening, and cells in state 1 are linear combinations of cells in state 0. Which means if you know certain cells in state 0, you can recover certain values in state 1, or certain bits, more specifically. So if you just recover a few values from state 0, you do have some information, some type of bias that's going to be influencing state 1. So if you recover anything, really, it could help you. But recovering the entire state does become more difficult, so I guess a very slight and marginal security win from Mersenne. Not great, not terrible. It's something. As for examples of RNGs going wrong, a very silly example was this paper published in 2012 by Lenstra and other people, mostly Lenstra. It was about analyzing RSA. Specifically, it was about analyzing RSA certificates, how the X509 one and PGP ones and stuff like that. And what they found was that, and for some context, RSA is just multiplication. Well, the public key of RSA is n, which is just the product of two primes. If you recover the primes, terrible stuff happens. You break the entire signature scheme, or encryption, depending how it's used. And what they found in their very, very large survey, they surveyed millions of certificates. What they found was that the way these primes were being generated was actually quite bad. Traditionally, you'd use what are called cryptographically secure pseudorandom number generators, which aren't Mersenne and LCGs. And these generators are very, very intensive, very, very complex, and they are very demanding as well. So people can get lazy, and they can use a regular PRNG thinking it's going to be all right, because, if it's uniform enough, what does it matter, right? But certain pseudorandom number generators have a very bad or very influential bias early on in their generation, meaning that certain bits are more likely than others. And when you're looking at the level of millions of certificates, of millions of primes, those slight biases, they really can influence it. And what they found was that there were certificates outside in the web, thousands of them, 12,000 roughly, at the time of this survey. By now, could be more. They found 12,000 certificates that shared a prime. This is catastrophic and hilarious as well, because you can just run GCD. You can just find the greatest common denominator of two ends, and if they share a prime, you found a prime. And GCD, unlike factoring, is a very, very fast and simple algorithm to do. You learned it in high school, if not earlier. It's very easy, very fast, and breaks the security of certificates sharing a prime. And yeah, what they found was that 0.2% of all certificates were vulnerable and compromised, and that was really, really bad in 2012, mind you. Now it could be worse, it could be better. It will be interesting to rerun the survey. The other very popular example of randomness being really bad is the PlayStation 3 hack from 2010. The exact details were presented at the Chaos Computer Conference of the same year, and actually the fact they were presented got the team into a lot of trouble because Sony got really pissed off and started legal matters against them, and they had a whole thing about it, which is why, in parts, the details of how this happened isn't really easily accessible, but the general idea was that Sony is effectively a certificate authority when it comes to their consoles, and all the games and software and firmware updates that get ran on PlayStation have to be signed by Sony using their private key. However, these signatures require a nonce, which is a variable that you never want repeated. You want it used exactly once, and that's it. But if you have very poor random generators, then it's possible these will be repeated. And if, in the case of signing algorithms, these get repeated, the private key gets leaked. The details of this don't really matter right now, but effectively, if the nonce gets reused, then the private key can be recovered from a simple linear equation, and that's bad. And that's really, really bad. And this is what happened with PlayStation 3. The group managed to find a few examples where the private key was reused, the nonce was reused, and they could recover the private key and could sign their own firmware and could run Linux or whatever they wanted on PlayStation 3. It was just that simple. And this still affects, I think, PlayStation 3 in some capacity. So, if you find an old one, you can run whatever you want on it. The TLDR of this talk, I guess, is that randomness is a very hard problem. Proper implementations are difficult. Things can go easily wrong. If you use the wrong constants, things really break very quickly, very easily. Synchronizing PRNGs is also a very, very big problem. You want sometimes multiple devices operating on the same seed, operating and generating the similar numbers. And when one generates, you want to update all the others. This is very common as a use case in authenticated encryption, where you want a server to be encrypting and generating lots and lots of nonces, but you also want these nonces to be independent of each other. You don't want to reuse, otherwise things break. And how do you do that when you're, let's say, Amazon, and you're generating millions of nonces, and eventually it's not just becoming probable that you're gonna generate a same collision, it starts becoming inevitable. And this is really, really bad. And the good news is cryptography as a whole is trying to slowly shift away from relying on randomness this much. And we're doing this in two ways. We're trying to make things more deterministic on one hand. The earlier mentioned signature algorithm, there is a deterministic variant where the nonce is generated based off of the message, so that two different messages can't have the same nonce. And encryption schemes, especially authenticated encryption, is also trying to go away from randomness. In this case, the nonce used in ASGCM is actually created based off of the associated data and the plaintext that's being used. So we're now moving away from generating random nonces to just having deterministic nonces, and this is really good. Other problems with randomness is just you can sometimes have unexpected sources of bias because your algorithm may not be performing in the way you want it to, and fundamentally, if you're just using hardware entropy, different environments have different entropy, and you might just be unlucky and your device may just have poor entropy. And that'd be all.
Okay, thank you very much. We're running a bit behind, so we only have time for 2 questions tops. So does anybody have any questions? Okay.
Wonderful.
I guess no questions. That's it.